All right, so this is going to be the lesson on how to work motion problems. And you should have one of these papers here in front of you, and if you could fill this out as we work, that would be fantastic. So to start off, there's a few things I want to talk about before we get into starting to actually do real problems. And there's some things that are some like little tricks and tips that I'd like you to kind of think about. So first off, in these problems, you'll have to identify your variables. And your variables, they can be a little difficult to figure out at first, but there are some tips and tricks. So first off, whenever you see a meters unit, that means that it must go to a distance. So if you have a number that's followed by a meter, you know it will be a distance. It has to be. And you'll see some examples of that later on. Meters per second is the only one that's actually kind of tricky. This could be either a VI or a VF. It could be either one. Just remember, VI means beginning and VF means ending. And you'll have to tell by the context which of those two things it actually winds up being. Meters per second, it goes back to being kind of nice where we have just one simple thing. It's got to be an acceleration. And then seconds, once again, that must be a time. And as you're working through these problems, just be careful. Watch out for phrases like at rest or stopped. These phrases are loaded, and that by that I do mean that they mean something is zero. Usually this one means that the VI is zero, because usually you start at rest, or but sometimes it can also mean VF is zero if it says it comes to rest, but usually they would say something different for that. Stopped usually means VF is zero. It's not 100%, but remember, use your context clues to try and figure out what those things actually mean. When you are going to look at an actual problem, I would suggest following a little procedure. Some of these steps you'll do kind of in your head, but it will help you organize the way you think about these problems, which will give you a greater chance of success. The first step will always be to identify your variables. Okay, this step is actually the most important step because it's how we start the problem. It's how we figure out what equation we need to use. And if you have trouble with this, it's likely going to cause you a lot of other headaches throughout this activity. So pay special attention when we do identify variables. Step 2, we are going to choose an equation. And I'll fill this one out a little bit more as we come across this in the example problem down here. Step 3, I'm going to ask you to please plug in and do so carefully. One of the most common mistakes I see is students who plug in things incorrectly and then just kind of go with it from there. Then lastly, we will solve, which will require some level of algebra every so often, so just be aware of that. Some problems don't need it, but other problems do. And once we have those 4 steps done, then usually our problem is kind of finished. If you look here in the middle of the paper, these are our 3 equations we talked about, or that you'll be using to figure these things out. Now, I do want to make a quick little change here. Because of the fact I forgot to change these, you may actually write these as D's. Do not worry about the delta x's. Those can be a little confusing, so we'll just leave them as D. Okay, so let's look at example problem 1, and I'll try and work through our 4 steps here as we go through the problem. So first off, we have a frisbee. It flies across the ground with initial speed of 16 meters per second. Now, as I read here, I'm just going to underline numbers that I see, because that'll be kind of helpful for us as we go through the problem. As the frisbee flies, it slows down from the air, experiencing an acceleration of -2 meters per second squared. The frisbee lands after a flight of 5 seconds. How far did the frisbee travel? All right, so in this scenario, the distance is usually referred to as how far. So when we are solving for something, if you see how far, It usually is asking for distance. So what I'm going to do first off is just write down what we are looking for, which in this case is distance. And then I'm going to circle back around to these other numbers I have underlined. So first off, if you look at the 16 meters per second, meters per second has got to be a velocity. We know that. So looking at the context clues of this velocity, I can kind of determine that the object is starting starting at that speed. So we can kind of safely assume that this is our VI. Because once again, it says it's starting with an initial speed. So that context frames it for us. As the Frisbee, the next number we have down here, I kind of boxed it by accident, is negative 2 meters per second squared. Meters per second, if we check up here again, that's an acceleration, so we kind of automatically get that one, which is kind of nice. And then finally, they also tell us over here we have a flight time of 5 seconds. So our t equals 5 seconds. So from here, we've actually successfully solved, or at least done the first thing up here. Next up, we're going to choose an equation. So we have to choose an equation from this little equation box, and we have to do so to determine what equation is correct. So when you choose an equation, you want to choose one that has all 4 of the variables that you have identified. Okay, so looking at the situation here, we have a D, VI, a T. If you look here, there's a VF. That tells me that I don't want to use that one. Right there's another VF. I don't have a VF, so I don't really want that one either. Over here, though, we do have the D, VI, T, A, T. This equation looks appropriate, so I'm going to write it down here. And that's the end of step 2. Step 3, I'm going to plug in and make sure I do so carefully. My distance is unknown, so let that sit as a D. VI is 16. T is 5. 1/2. A is negative 2. And then T, once again, is 5. And make sure you don't forget your square. From here, we're actually pretty fortunate. This is already solved out for us. So we really could take a calculator and just plug this in exactly how it looks, and we'd be able to solve this. So plugging in 16 times 5 plus 0.5 for 1/2 times negative 2 times 5 squared will give us a final answer, and that answer will be correct. So in this case, D is equal to 55 meters. Okay, notice once again that the acceleration here was negative. This is negative because the object is slowing down, and that's actually pretty important. All right, let's look at another sample problem. Okay, so in this case here, this is a 3-parter, and we'll look at what this actually is going on here. So let's just read through it once, and I'll underline numbers once again, or any at rests or stopped. A car is moving down a street at a constant velocity of negative 20 meters per second. A child suddenly runs into the street 60 meters in front of the car. If it takes the driver 0.7 seconds to react, how far will the car go before he applies the brakes? So in this scenario, we have to be careful about this distance right here. This distance is not talking about the car's motion, it's talking about the car's position relative to the child. So in this scenario right now, we know the car is roughly about 60 meters away from this little kid. And right now we are checking to see, does the kid get hit by the car? That's what we're trying to figure out. So we don't want to set our distance equal to 60 meters for the actual car. Otherwise, we're guaranteeing this kid gets hit. Instead, we're going to be checking against that number as we go through the rest of the problem. So with that in mind, we will kind of put like a little exclamation part there. We're checking against that. It's not a known we want to set. But otherwise, let's pull out what knowns we know. So here it says how far will the car go. We're looking for a distance again. That how far clause, always referring back to a distance. Here we have 0.75 seconds. We know seconds are always times. But up here we have another velocity. And looking at this thing here, this may be a little confusing at first because they don't necessarily tell us whether this is starting or ending. But they do tell us that it's constant. And remember, constant means that it's not changing. So in this one scenario, our VI is 20, but so is our VF because the object isn't changing speeds. So we can actually set that equal to both. Now if you notice here, we have D, T, VI, VF. We don't have any A. So when we go back to our previous paper to look at our equations, we do not have an A. That's not good. Neither is that equation over there. But in the middle here, we have D, VF, VI, T. And in our situation over here, we have, once again, D, VF, VI, T. That looks like it's the one we want to choose. So we are going to go with that particular problem, well, with that equation. So let's look at it then. Write it down. D equals 1/2 VI plus VF times T. Plugging in carefully, we have D equals 1/2 times the quantity of 20 plus 20 times 0.75. And once again, this is solved for us already. So once we have our equation, we can just plug this into a calculator again, and we will get an answer. So putting it exactly as I have it written gets us this answer. So D equals 15 meters. So after the initial part of the reaction time for the car to figure out, hey, I need a brake, the car has actually traveled a little further. So right now, the car is 45 meters total away from the kid as it progresses to the point where the driver hits the brakes. So we're not quite done yet because we don't have a conclusion. We want to figure out, does this kid get hit? So let's look at the next question with letter B. It tells us the car begins to accelerate at -5 meters per second squared. How long does it take the car to stop? As a reminder, how long, this is the first phrase we're seeing at this time, means that we're trying to look for a time. So we are looking for how long it takes the car to come to a stop. Here we know our acceleration. Our acceleration is -5 meters per second squared, and this negative is important because we are slowing down. If we were accelerating or going faster, that wouldn't be appropriate for our kid because that would mean we are definitely killing this kid. And in fact, I actually missed a word. I missed stop. Stop is our next word, and stop implies that in this case our VF is 0. And that's all I can get from letter B. But there is one additional thing that I can pull down from letter A. We know what the car was doing before the brakes were applied, so we actually also know that VI is 20. Now, the other problems that you'll be asked to solve today, they won't ask you, or they won't be continuous problems like this one, so everything will be self-contained. This one's kind of special. But knowing these things, we now are able to choose an equation, which we will do in the second part of this little lecture thing.